Start the review again. We've been talking about the first chapter was about the mass spec. Okay, there's another example I want to go over. But before we go over that one, let's try to remember one thing. So I want you to remember this one. So whenever you have an alcohol, okay, that means you have some carbon there. Okay, you have a hydroxy group on it. Okay, so if you have a hydroxy group on your carbon, will become your alkyl compound over there. Okay. So if that is the case, when you do the mass spec, as we remember from the last time a long time ago, we'll make us like a small fragment of your compounds by doing like high energy electron bombardments over there. So you can think about those are the one that is most likely broken apart. This is what we call alpha cleavage. Because whenever you have the carbon that has that specific, the hydroxy group over here, and the one next is the one that you're gonna break. Okay? So we call this alpha cleavage over here. So whenever you do this is the only thing you really have to just remember. But this is something you don't have to remember. But whenever you do this one here, they break apart in a radical form. It's a cation over here, right? And if you do this one more specifically, you can do this one here. But the most importantly, you're gonna lose this part of the compound whenever you make the fragments of this one in mass spec. Okay. I'm going to talk about this one obviously in the exam because you have another scenario you can do. This is what we call dehydration. Okay. So whenever you have certain radical cation radical, this will become very unstable, right? But in this case, the second scenario, they will just do dehydrating, just getting the water out. You see this, the hydrogen and the hydroxy group, and they just dehydrate by just getting hydrogen over here. Just the over here. So there's two scenarios I want you to remember for the exam. Okay. So this is be the one that I'll put on the exam for sure. This is important because this is one of the case we have two possible scenario. So the question will be like, I'll give you one example. And I'll ask you to choose if that compound went through this scenario or this scenario in their fragmentation. Okay, so I'll show you the example here. So if we have some alcohol, looks like this. Okay. Okay. So if you have this type of 2-methyl 3-pentanol over here, you'll find some the graph looks like this. Okay, here. Okay, and then this is mass spec. Okay, mass for charge ratio. Okay, so the first. And then literally this is the same as what? Once again, molecular weight, okay? Because the charge will be just +1, okay? You guys remember this? One become a radical, the other become cation in the fragmentation. So the one that the positive charge will be catch in the detector, we're gonna find those numbers on the graph over here, okay? So if I give you this one, just once again, I'll ask you in the exam, the first, the second, if it was just the alpha cleavage or dehydration. So you need to look at the graph and find out which case we have for this compound over here. So first thing what you need to do is this one. You try to get the molecular weight first by looking at the structure in the exam. Okay? So if you look at this one over here, has here over here, right? And then we're gonna build the hydrogen over here. Okay. So just try to count all the numbers of carbons, which is what? 1, 2, 3, 4, 5, 6. Okay. Hydrogen will be what? 6, 7, 8, 10, 10, and 13, right? Sorry. Yeah. Oh no, there's one more here, right? 14. We have one oxygen here too. Okay. So try to get the molecular weight just using chemical formula over here, which is 6 times 12. Okay. That would be 72, right? Plus 1 times 14 is 14. Okay. And then we know this is 16. It's 1 times 16. So approximately it will be about 1 and 2. Okay. So if you look at this number here, basically you expect what might be your molecular ion or parent peak on here, but you don't find here. So there's got to be something that we need to have explain why, and that is this one or this one. Okay. So if you have a molecular weight, should be around 1 or 2. So you gotta see something over here, but you don't see it. But the one you see here on the far right one is 73. Okay, and also the second far the right one is 59. So let's try to do alpha cleavage over here. So alpha cleavage here will make. So if you have this carbon here attached to this hydroxyl group over here, then meaning either this is going to break this one or this one, if it's number 1. Okay. If it's dehydration, they're going to lose the hydrogen here, and they'll lose about 18, because the molecular weight of water is 18, right? So whenever you do 1 or 2 minus 18, there will be 84. Okay, but you don't have any peak that on 84 here. So most likely this is not the case we're looking for here. But let's double check if it did really alpha cleavage on this fragment here. Okay. So first of all, when you break this one apart here, this will be CH2. This radical you're going to lose from this cutting here, okay, in this case. So I don't know if you guys remember from the last time, this will be 29. 2 carbon and 5 hydrogen over here, right? So whenever you do 1 or 2 minus 29, what's that? 73. It's right here. Makes sense, right? And then let's check this one too. And here, we're gonna cut it over here, right? So this will be 3 carbons, and 1, 2, 3, 4, 5, 6, 7. So 3 hydrogens on here and 1 over here. Okay, there'll be 7 that you're gonna lose. Okay, so that's about 36. This is 12 times 3 is 36, plus 1 times 7 is 7. So it'll be 43. Okay, so 102 minus 43 is 59. You have a 59. Okay, so this is indeed what for good example of alpha cleavage, but not dehydration. So this will be on the exam for sure. Maybe not the same, but very similar compound. Only thing you have to do is try to cut on the alpha cleavage position or dehydration, which is just negative 18. And if that comes with any number you see on the peak, that will be the case for what happened to the compounds in the mass spec. Does it make sense? Okay. So please remember this one, okay? This article 1, I'll try to put on the exam, which is quite important. So I think that's pretty much it for the mass pack. Okay, let's go to the IR. Okay. So the if you guys remember this one, okay. If you guys remember this one, maybe I know it's been a while. Like I said before, you don't have to worry about this one too much. This is I want you to remember this one for the exam. This is the reason we call what? You guys remember this? The below 1500 in the IR. This is IR now. What is the one below the IR? Is the fingerprint region. Okay? So remember this one for the exam, okay? So anything that below 1500, okay, is the fingerprint region here. We call this fingerprint region because whenever you have any compound that shares the same pattern on the fingerprint region, that almost they're almost 998% chance they're same compounds. So like a fingerprint, we know what that is by looking at the peaks on the fingerprint region here. So, but at least remember the definition of it, okay? What it really means. So this is where you can find those ones over here, and then you're going to have some this one, okay. And then this is where you can have this one. So if that is the case, I'll give you one example. This is the okay. If I give you, okay, did you copy this? You good, right? Okay. And I'll give you this one over here, okay? And then we'll try to give you with 3 examples in the exam. So this is maybe hexane, hexene, or hexine, okay? So I'll give you 3 examples and choose the right one by looking at this one over here. Once again, I think it will be quite straightforward because I'll give you the table for it. So if you just look at the table carefully, you probably know what those supposed to be mean anyway. Okay. So if you look at this one over here, if you look at the table, this is the very common for any carbon-carbon alkane compounds. Very narrow but long, somewhere between 3,000 to 2,800. So this is for everything. Those all 3 will have like carbon and hydrogen in a bond. So this will be the common peak you see even among those 3 all together. But another thing is they have a little bit of weird long peak over here. But most importantly, you have some peak between 2,800 and 2,000 here. Okay. That is, if you guys remember this just before, it was about like this one. Okay, we just did it together, right? Then this is a good indication of what? It will be hex sign, right? So if you have a 3 multiple choice to choose, I'll give you this graph over here. This will be something you'll see over those all 3, but this is only for hexine, right? So in this case, you'll be able to know, oh, because of this one, it should be this one. And once again, this one you don't have to worry about too much, but this is good enough for finding the best choice among those 3. Okay. Makes sense, right? Okay. So if that is the case, if I switch this one to here, okay, what would that be now? Can you guys guess? Maybe 1 or 2 minutes. So I switch the peak over here. It's slightly longer, but more close to the 1,500. Okay. then what would that be? Can you guys guess? Hexane, perfect. Because this is where you can find the double bond. Okay? So I'll give you the choice, and then it will be quite obvious if you look at the table very carefully where the peaks are and where the double or triple bond indication. But the hexane doesn't have a double or triple bond, but this one has double, this one's a triple, so you'll be able to know. So if I don't show you any peaks on these two, but just this one and nothing there, and there's some after below 1500, that will be just simply hexane there. No peaks on either indication of double or triple bond. That makes it purely just hexane. Okay? Make sense, right? Good. Okay. Let's do one more. So I think the IR-wise, I think you just need to know how to look for those peaks. That will be pretty good enough, I think. Next one. Okay, I'll give you. This one, and your choice is between these two. Okay, great. So maybe you can try this one. The same knowledge, same principle we used for the previous one. I'll give you two. Choose which one this will be in this peak. So this is a one broad, quite long, maybe it's too long, but around like a 2,800 to 3,000. Some are pretty broad hand. And this is another one between 2,000. Okay, so just give it 1 minute. Think about it, which one would be the right compound on this IR. Try to think about where the peaks are and look at the chemical structure of these two choices and pick that one. Okay, if this is number one, this is number two. Which one is it? What do you think? One, perfect. Great. Because this is, once again, this is where you're gonna find what? This one. You guys remember this, right? And this is also the one common on those two. So this one actually doesn't tell you much, but this one does. Distinguish from this one from here. Because this is just the methyl group, these two carbonyl groups that makes the ketone. But this is a more carboxyl group like OH group, which is hydroxyl, that is perfect match on this peak right here. Okay? So if it's multiple choice, you can choose the right one for sure, right? Okay. Very good. Okay? All right, so let's move on. Okay, here's the next one we can try. Let's try some carbon NMR here. This is okay, and I will give you this one. This one. And this one. So this is 1, 2, 3. Okay. And this is a carbon 13 NMR. and try to find out which might be the best choice among those three. First thing you need to look at is if those carbons are equivalent positions. So how many signals will be there is first thing you need to look at, because there's 3 signals right there. Okay. So you need to look those 3 and see how many signals should be there. Okay. That's the first thing you need to do. For about 1 minute. Okay. So you have a 3 choice to pick one, the 1, 2, 3, and try to look for how many signals should be there for each, and then where they're supposed to be located in the carbon-13 NMR. That's the point. Okay. Okay. So what do you guys choose? Is it 1 or 2 or 3? 1, right? Is it 1? Okay. Perfect. So here's the thing. Let's try to look at 2 and 3 first. Okay. So if you look at this one over here, how many signals should be there for this one? There will be only 2 signals. Okay. Because I know we have 3 carbons, so technically speaking, you should have 3 signals for each carbon, here and here, here. But the thing is, this is what? Symmetrical plane in the middle. So those 2 will be overlapped on the same position. So there will be only this one and this. So 1, 2 signals there. Okay. So this will have 2 signals. Okay. This one has the terminal here, but the chemical environmental wise, these 2 are not the same position, because this terminal carbon attached to the intermediate carbon that attached to the oxygen, that is the carbon that attached to the carbon in the carbonic groups. So these 2 are same terminal carbon, but will not share the same position, slightly different, because the electron de-shielding power will be different on these 2 carbons because of the different carbon neighboring in those terminal carbons here. So, but that makes sense. This one these 2 are slightly still different. This is the one that attached to the oxygen here will be a bit more withdrawn this way in the electron wise. So somewhere here too. And there's another one in carbonic group will be somewhere in this region here, which is most withdrawn, like de-shielded carbon you can ever think of. Then you should have 4 signals. Okay? So unlike this one, these 2 will not overlap. They'll be slightly different because of the slightly different chemical environment over there. These 2 from here. But this one will have 3. Because they're all in different chemical environment too. Then 3 carbons there. So there will be no symmetrical plane you can do. So this is the one that has to over here, but quite well withdrawn on this way. So the terminal carbon should be somewhere in here, but we don't more on the left side because of the carbonic groups that has quite of a power to withdraw the electron toward themselves. And this one is attached to oxygen, also very de-shielded, right? So somewhere here. Okay. And this one obviously the carbonic group, which will be most de-shielded carbon you can think of. So there's 3 picks matches to number 1 the best. Okay. Makes sense, right? You good? Okay. Great. Yes, great. Okay. Then try to do this one. So we have this compound. This is the one we tried last time, and we do proton NMR here. Okay. So as you can see, the scale on your delta is very smaller now, only 1 to 10 or 12, not 220. So then you have some peaks over here and here, okay? And then I just want you to find out these two will have how many peaks on each signal. So there will be two signals here, okay? But think about how many peaks on each, okay? Here and try 1 minute, and let's do this together. Okay? And also, don't worry about the position too much. Okay, I'll give you the table. Okay, only thing you have to know is what I'm asking you for right now. That will be the one you're gonna solve for in the exam. So just tell me how many peaks on here and here. You don't have to worry about the position. I mean, it will be better if you know, but it'll be in the table anyway. So don't memorize the numbers, okay? But you kind of know where, relatively speaking, those peaks should be located. Okay, 30 seconds. Let's do this here. Okay, so if you look at this one over here, as you know, this is somewhere you can get some terminal carbon attached to hydrogen ones over here. This is somewhere you can have some ones on the carbon attached to the halogen that nearby the hydrogen. So this is from here to over here. Okay? It kind of makes sense that if you look at the bromine, will kind of withdraw a lot of electron density toward themselves. So it'll be more, those protons will be more deshielded by this one. And this is kind of one carbon further away from than this one. So it'll be more on the right side, which is more shielded with the electron. Okay? So if that is the case, I hope you guys remember n+1 rule. You guys remember this one, right? You guys remember this n+1 rule? So in this case, those the one that has neighboring with the 2. First thing you need to know is why those two position hydrogens are non-equivalent to each other. Because the condition, the environment is totally different from those protons and those protons over here. Because of those are the protons where you have a bromine neighboring on the right side. On the left, you have a carbon and with the third hydrogen in it. But these protons are neighboring only one carbon with the two protons on it. So those are not equivalent, so the two signal, that's why, first of all. And then those each, and for those each will be the same because there's no chiral center on the other neighboring carbon. You guys remember homotopic protons? So these two, those 3 protons were on the same position in these two, but these two will be non-equivalent to each other. But the one on the same carbon, there's R. Okay, so then you need to remember the n+1 rule. That is where you can have this one is neighboring with the what? 2 protons over here, right? This peak is this one, right? Okay, and this neighboring with the 2, so it'll be n+1. 2 plus 1 is what? 3, right? Perfect. So there will be 3 peaks on this signal. Okay, makes sense, right? And for this one, this is this one, but it's neighboring with 3 protons on the neighboring carbon. So 3 plus 1 is what? 4. So it'll be 4 peaks over here. So if okay. So one thing additionally I want you to remember is there's the peak ratio, triplet and quantet over here. You just need to know the Pascal's triangle. So if you have a 1 over in the top, you try to fit the 1 to the left and right. So if you go from here, the 1 becomes 1, 1, because you're gonna fill the 1 from the left and right side. And then you just add 1, 1 over here at the middle, and you fill the 1, 1 again. Okay? And then you do 1 plus 2, 1 plus 2, 3, 3, and 3 to 1 on the side. So we just keep going. 4, 4, 6, 1, 1, and keep going. So in this case, you have 3 peaks over here. So there will be 1 to 2 to 1 shape, okay? Ratio shape. And this will be 1, 2, 3, 3, 1. Okay? So this is what this will be looks like. Yes. This will look like this. Okay? I want you to remember this one. Simply doing Pascal's triangle will help you understand what it should look like. Okay? Okay. Let's move on. So I'll try to do more NMR over the next Monday, and also, yeah, I'll give you some probably over my Canvas in the weekend. So there's the next one we can try is maybe probably give you some those compounds. Okay. I just want you to find the conjugate compound. If it's 1, 2, 3, and 4. Okay, I want you to find the conjugate compounds among those 4. Okay, so what do you guys think? What are the conjugate compound among those 4? 1, perfect, and 4, perfect, great. So only thing that you need to know for looking for a conjugate compound is if you see like a double bond and single bond is alternating to each other, and at least in the one part of the compound, that is a good example of conjugate compound. Great. So I'll move on here. We have a good understanding of what this conjugate compound means. Then one thing I cannot so here's one thing we learned before. Okay, can you guys? No, wait a minute. I'll show you. Okay, let me give you this one first. Before we do this one, let's try to do this one first. Okay. So, do you guys remember 1, 2, and 1, 4 addition, right? So, not just one, but there will be 2 products. So, the first one looks like this. Okay. 1, 2. Okay. There's another one. Oh yeah. And another one looks like this. Okay. It's 1, 4. Okay. So just try to remember, because they can do this because there's a double bond and single bond, and this can do what? This move and move and move. They can make some alylic carbocation on this position, so they can attach to the end as well. And this one, okay? So we learned this in the kinetic control, thermodynamic control. You guys remember this? Kinetic control, thermodynamic control. So just try to remember this too. So whenever you do chemical reaction with the conjugate compound, there will be 2 products, not 1, okay? And then if that is the case, maybe can you guys try this one? Okay, I'll give you about 2 minutes and try to find out the products. Okay. This is also what we tried before. Yeah. And this is very important for the exam too. 1 or 2 minutes. It will take some time because there'll be not just 2, but actually 3. Okay, think about 1, 2, and 1, 4 addition again. Okay, so let's do this together. Okay, so there's a 2 scenario you can do. You can actually add 1, 2, 1, 4 here, here. So technically there will be 4 products, but I will tell you why there will be 3 only. Okay, so the one you can do. So we'll do this one first. Okay, 1, 2, 1, 4. So maybe this is the 1, 2. Okay, so this is the first one. So this is 1, 2 addition over here. Okay, and the 1, 4 will be this one. Okay, 1, 4. You see this one over here, right? And but the thing is, you can actually do it from here too. So we're gonna do 1, 2, 1, 4 here and as well. Okay, so let's do 1, 2. So this will be okay. This is 1, 2, and also you can do 1, 4. This is 1, 4. It's 1, 4, 1, 2. Okay, you see, right? So we did it here 1, 2, 1, 4, 1, 2, 1, 4. These 2. Okay, you see it, right? We did a 1, 2, 1, 4, 1, 2, 1, 4. There'll be 4. Okay, that's why we have a 4. But can you guys see something here? Do you guys see something over here? These 2 are same. Do you guys see it? Yeah, same. So chlorine, methyl group, double bond, chlorine, methyl group, double bond. Just flip it. Okay. So there's a 4, but those are the same. So we 1, 2, 3 compound. The products there. Okay. Because of the 1, 2, 1, 4 addition. Yeah. So the okay. Please remember this one for the exam. This might be on the exam. Let's do one more and the extra credit. So I'll do more problems on Monday as well. So one thing I might ask you to do for prepare for the exam is just study them over weekends, and you might have more questions, right, over the weekend. You can ask me on Monday as well. We still have some time from Monday and Tuesday as well, so you should be better prepared for the exam. Okay. So maybe another question I might put on the exam maybe looks like this. Okay. Okay. So if I give you these 3 compounds, okay, what might be the only diene can be used for Diels order reactions? Okay, so I'll give you 3 compounds over here, and then I'll tell you which one might be the best one for Diels order reactions. So if you have a diene, those 3 dienes, react with the dienophile. Okay, so choose the best one. I mean the one that works on the Diels order reaction. This is 1, 2. Okay, I don't want to sacrifice the extra credit time, so I'll finish up quick here. So which one do you think is the best one? this one. So the this one as trans and cis, meaning that this diene should be able to rotate. So they can be in this form instead of this one. This won't be able to do the other direction because they need to have they need to have this type of what can I say, approach. So it has to be in the cis form, as a cis form. By placing it as trans like this, you can actually rotate it. There's no problem for this compound. But what about this one? Can you rotate this one over here to make it cis? No, because it's a bicyclic compound. It cannot be rotating this part. So this is not good. Okay. So what about this one? We already have this one already in the cis form. But the problem was there's two methyl groups like all groups on this diene structure. There will be too much of a static hindrance occurred. So they actually turn into S transform automatically. So they cannot sustain this form at a long time. So this is not good for the other direction either. But this one is the best one because there's no static hindrance problem here. This is only single bond, so you can just rotate, but this one cannot, this one cannot. Okay? I will stop here today. Let's do